let's continue. So, ano to siya, no? So, this is the average permeability if the soil is layered parallel and the flow is ano siya, no? Horizontal flow and the soil is layered. But if still layered soil, no? And the flow is perpendicular, meaning in this figure, this one, no? Sorry, hindi ko siya makakuhan. Okay. Gamay po siya. Alright. So, ingani siya, no? But if the soil is layered soil and the flow is perpendicular, so the head loss is different in each layer, no? So that delta H1 plus delta H2 plus delta H3 is equal to delta H. And Q, discharge for this one is equal, no? The Q, the total discharge per unit time is Q1 plus Q2 plus Q3. And the area are also equal for this, no? That A1 is equal to A2 is equal to A3 is equal to the total area. So that the equivalent permeability will be very close to the lowest permeability. So in this layered soil, still, no, the basic concept is that Q is equal to KIA, but the same Q, no, for each layer. So kaning Q1 is equal to Q1 I1 A1 and also equal to Q2 I2 A2 is equal to K3 I3 A3. Since A is equal to A1 is equal to A2 and A3 is equal to A3, the area, this is K, yes, since area is the same, no? Actually, since gikan ani siya, this is KIA. So, K, I is delta H over H because the flow is perpendicular. So, this is your L or like the total H nga daganan sa tubig, no? And since pareha man sila og area, so ma-cancel out ra gyapon ang area mo nang kanira gyapon ang mabilin, no? Say we consider the first two terms and gikan ani we will get the relationship in terms of delta H1, no? Kasi gikan ani cross multiply ka, so mahimo siya og H1K delta H over K1 H. And also kani o kanina pod, no, is this one, no? Delta H2 is equal to big H2 sub 2 times K over K2H delta H. And this one na pod siya, kanina pod. And kaning third is this relationship. Now, delta H3 is equal to H3K. So that since delta H, the total head loss is differ in each layer. And the total head loss is equal to the sum of the individual head loss, no, per layer. So substitute this one kani in here. Substitute. So, mahimo na siya o this one, no? Mahimo na siya kani. And we would like to get the value K in terms of, di ba? So, actually, ma-cancel out ni siyang delta H, this one, the H, since naman siya both sides. Then, kani siya ang mabilin, di ba? 1 or H over K, kani siya is mahimo siya ani. Then, in terms of K, in terms of K, mahimo ni siya yani. So, this is your final relationship to get the value of the average K for perpendicular flow. If the flow is perpendicular, na siya sa ibabaw. Layered soil but the flow is perpendicular. While ganina, the flow is parallel or parallel sa layer, no, sa soil. This is the layer of the soil, horizontal, parallel. This one is layer of the soil, horizontal. The flow is perpendicular. So we have this example, no? Example is a horizontal stratified soil deposit consists of 3 layers, each uniform in itself. The permeabilities of these layers are 8 times 10 to the negative 4 centimeter per second, 52 times 10 to the negative 4 centimeter per second, and 6 times 10 to the negative 4 centimeter per second. Their thickness are 7, 3, and 10 respectively. Find the effective average permeability. So this is actually the K, no? This is K, ang gipangita. The average, actually small K, no, of deposit in the horizontal and vertical direction. So, in the horizontal and vertical directions, so meaning if the flow is horizontal, no, the flow is horizontal and flow. So, this will be our first objective, no, to get the average K. And if the flow is vertical directions, no, kung flow, so this is the flow, then this will be our second objective. Now, what is the value of average K? So, to get this first, the value of the parallel flow, we have to use the formula, this one, no? This formula. So, from that one, mani siya ang given. Then, actually, directly, you can use the formula directly. Diba? This formula. Or actually, this formula or this parehara na siya. But in the example, he uses the first one, no? So, he denoted as KH, no? Or horizontal, or this is K sub X, no? So, actually, substitute naman ka, no? K1, H1, then plus K2, H2, no? From the given. Then H1, that is 7 plus 3 plus 10, or H1 plus H2 plus H3. You have to add this height of the height of the layer of the soil, no? Then this is the average permeability in the horizontal direction. In terms of centimeter per second, it is times 10 to the negative 4. But in millimeter per second, this is 13.6 times 10 to the negative, I guess this is 8. No? Or not 8. I think this is, yes, 8. Then for the vertical direction, we have to use this formula, this one, no? Meaning the flow is perpendicular. So, using the formula, that is, he denoted this as KV, K sub B, or K sub Z. So, the formula is this one, diba? H, the total H. So, the total of this one is 7 plus 3 plus 10, this is 20. This one is the total or the big H, and H individual height of the layer, no? So 20 over yang separate ang 10 to the negative 4 because these all are 10 to the negative 4, no? Times 7, the first height na 7 over 8, no? Plus 3 over 52 plus 10 over 6, so that the answer is, in terms of millimeter per second, 7.7 times 10 to the negative 8 millimeter per second for the effective average permeability in the vertical direction. No? So this is near to or closest to the smallest permeability. No? While this one, this is closer to the highest value according to the very close to the largest permeability. The 13.6. No? Mas dool siya sa katong more than siya, no? Than the two smaller permeabilities, no? Then let's proceed to different hydraulic conductivity of some soil. Some soils we have after the Casagrande and Fadum in 1939. We have the soil types, the clean gravels, clean sand, and gravel mixture, very fine sand, silt, and clay soils. Notice that from clean sands to clay soils, kagamay ang permeability, no? In centimeter per second, ang clay soils na lang from 10 to negative 7 to 10 to negative 9. So, grabe kagamay gud ang permeability. Meaning, maglisod og lusot ang water. So, drainage conditions, we have the assessment, no? Clean gravels, that is good. Hangtod sa clean sand and gravel mixtures, good. But, pag sugod na sa very fine sand, poor na siya. And the clay soils practically impervious, meaning impervious is dili siya gaka lutsan o water, no? We have still a description or a differentiation of the different soil types, no? Actually, mo ra man siya gikan aning sa table, magi kuan lang siya, gi-graph lang, no? From 10 to the 0, yes, this is 0 to 10 to the power of negative 11, which is this time practically impervious na siya. So, we have drainage, yes, very fine sand. So, let's proceed to the empirical correlations of hydraulic conductivity. The granular soils, the velocity of flow, so we have here I guess this is the formula of the average velocity through a tube. So where R is the radius of capillary tube of sectional area A, and Q is the discharge through the tube, V is the average velocity through the tube, and mu, this is the coefficient of viscosity. So, extensive investigations of filter sands by Hazen in 1892 led to the equation K in meter per second, that is equal to CDE squared. So where DE is the characteristic effective grain size, which was determined to be equal to D sub 10 or 10% size. Now, according to Hazen 1892, lahi po ang iyahang equation or formula. This is, I guess, the C, this is the coefficient, no? Coefficient, which is, nani siya a numerical value, no? Ang C times the effective grade size, which is D sub 10, this D squared. So, maupod ang iyahang formula. This is for granular soils, no? Average velocity through the tube can be expressed in this equation. Q, this is the discharge through the tube divided by A, which is the area of the tube, or the cross-sectional area, no, of the tube, is equal to the unit weight of the water times R squared. R is the radius of the capillary tube over 8 mu is the coefficient of viscosity, is equal to unit weight of the water times I, this is a hydraulic gradient, D squared. I guess this is the diameter of the capillary tube divided by 32 mu. Alright. For the pumping well, this is the well, then we have this two observation wells, or it's like piezometric tube. Then we have the height h1 and h2. So from the radius, or from the center of the pumping well to the center of this tube, this is r sub 2. The inner, no, the inner, since this h2, so r sub 2. The outer h1, the height. So from the center of the pumping well to the tube, no, outer tube, that is r1. So that the average permeability can be expressed in this equation, no, is equal to 2 point, this is na 2000, I guess this is 2.303 Q log Q is the discharge, no, in volume, no, volume per unit time. Radius 1 over R2 over pi H1 squared minus H2 squared. Pump well in a confined aquifer. We have this pumping well. Then confined siya, meaning confined is we have impermeable stratum or impervious layer in another impervious layer na pod, no. Then yes, kanang confined aquifer, meaning na ay aquifer diri sa between sa impermeable stratum or impervious layer, no. So that if this is the situation, no, we have the pumping well in confined aquifer. This is the formula. We have K is equal to, or the coefficient of permeability, K is equal to Q log 10 times R1, not times, Q log 10 close and open parenthesis, R1 over R2 over 2.727 big H. The H is the layer of the, from the second impervious layer to the katong to the top of the aquifer, no, another aquifer, times H1 minus H2. The same concept actually with this one, with R1 and R2, and also H1 and H2. So this is the formula. So much for this coefficient of permeability. Let's proceed to the seepage and flow nets. So this one is, the application of this one is for the for the dam, example for the dam, or kuan sa retaining wall, no? There is water, no? The presence of water. So we have the effects of seepage. The interaction between soils and percolating water has an important influence on the design of foundations and earth slopes, meaning soils and the percolating water. So those water, from the word itself, seepage, meaning the tendency of the water, the ability of the water to travel, no, sa between soils, no. This has an important influence on design of foundations and earth slopes. The quantity of water that will be lost by percolation through a dam or its subsoil. As water flows through soil, it exerts a frictional drag on the soil particles, resulting in head losses. Then frictional drag is called seepage force in soil mechanics. Alright. It is often convenient to define seepage as the seepage force per unit volume. It has units similar to unit weight, which we will denoted J sub S. If the head loss over a flow distance L is seepage force, delta H is given as, so we have the seepage force per unit volume, which we denoted as G sub S, is given as delta H. This is the head loss times the unit weight of the water over L. L is the distance, no, path of the water in the soil, no, asa mo travel ang water, is equal to I times the unit weight of the water. So we have here the downward seepage and the upward seepage. No? So if the seepage direction is downwards, then the resultant seepage stresses are in the same direction as the gravitational effective stresses. So the the resultant seepage stress, no, kung downward seepage, meaning the same direction with the gravitational effective stress. So this is the formula. Now stress bar Z is equal to the unit weight of the soil Z plus the hydraulic gradient Z times the unit weight of the concrete. Gamma prime. Gamma prime, this is the buoyant unit weight of the soil. No? Is equal to the buoyant unit weight, or this is gamma prime Z plus J sub S. This is the seepage force per unit volume times Z at certain distance, no, from the top. Then in case of upward seepage, they are opposite direction. So i-minus lang siya, no? This positive here will be negative or minus, no? Minus lang. Because different direction na siya sa gravitational stress. Effect of seepage on structure. So we have here, say this is a retaining wall. Then we have here a water, na presence of water. Then effective stresses increases as it goes downward, di ba? Then lusot ni siya diri, effective stresses decreases upward, no? From the formula itself, this is minus. So mo nang the stress is will decrease if the direction of the seepage is upward, no? Foundation failures due to piping are quite common. So there is, we call as foundation failures because of the seepage, no? As I've said, no, the water is the number one kalaban sa structure, no? Prepping is a phenomenon by which the soil on downstream sides of some hydraulic structures get lifted up due to the excess pressure of water. The pressure that is exerted on the soil due to the seepage of water is called the seepage force or pressure. Effects of seepage and effective stresses near a retaining wall. So the soil on downstream sides due to get lifted up, meaning the soil, no, on the downstream, this part here get lifted up because of the excess pressure ning sa downstream, no, downstream side. So mutaas ang tendency ani mutaas ang yuta diri because of the excess pressure diri, no, because of the too much water pressure. So tendency mo nang mo kuan ni siya mo overturn ni siyang retaining wall in this direction because of this pressure of the water on the downstream, I mean upstream, this one. So muna siyang effect of the seepage on the foundation structure. Another effects is in the stability of slopes, the seepage force is a very important factor. Shear strengths of soil are reduced due to the development of natural stress or poor pressure. No, shear strengths of soil are reduced because of the too much, no, poor pressure. Meaning poor pressure, this is the presence of water, no, in the soil, no. That is why there is tendency nga mugamay, no, or mawala ang stability of the slopes. A detailed understanding of hydraulic conditions is therefore essential for a satisfactory design of structures. The computation of seepage loss under or through a dam, the uplift pressure caused by the water on the base of a concrete dam, and the effect of seepage on the stability of earth slopes can be studied by constructing a flow nets, no? That's why we have to understand, no, the behavior of the seepage or this water in this structure, like the concrete dam, no, or retaining walls. We have also this quicksand, no, condition. Quicksand forms in a saturated loose sand when suddenly agitated. Quicksand forms, no, in saturated loose sand, no, when suddenly agitated. So manang there is a formation of quicksand. Meaning of quicksand is kung kita niyo sa movie katong mo makakuan sila, no, kanang murag mo absorb ang sand of object, or like kung malubong ka dito murag maglisod na ka og hawa. So that is quicksand. When water in the sand cannot escape, it creates a liquefied soil, no, and loses strength and cannot support weight. Yes, dili siya cannot support weight. So that is why malubong ka dito, padayon jud kag lubong, no? In the case of upwards flowing water, seepage forces oppose the force of gravity and suspend the soil particles, causing loss of strength. Then the cushioning of water gives quicksand and other liquefied sediments a spongy fluid-like texture. Objects in liquefied sand sink to the level at which the weight of the object is equal to the weight of the displaced soil or water mix, and the submerged object floats due to its buoyancy. So, ang katong objects nga mabutang dito sa quicksand, may liquefied na, no? Musink gid siya until maabot sa level nga ang iyang weight will be equal to the weight of the displaced soil or water. So manang mo-float na siya, no? And submerged subject due to its buoyancy. Nagyapoy buoyancy ang katong liquefied quicksand, no? Mechanism. An upward flow opposes the force of gravity and cause to counteract completely the contact forces. Effective stress is reduced to zero and the soil behaves like a very viscous liquid quicksand condition. Then this condition occurs in coarse silt or fine sand subject to artesian condition. And quicksand is because the coarse silt or a fine sand. So this is the mechanism of a quicksand condition. So to better understand this one, you may click this YouTube link. No, there is a video about this quicksand. To continue, no, at the bottom of the soil column, so there is stress. I mean, the stress is equal to the unit weight of the soil times the length. This is, I guess, this is the path of the water in the soil. So during quicksand condition, the effective stress is reduced to zero. So the critical hydraulic gradient, is just equal to delta H. This is the head loss divided by the L. This is the path of the water in the soil is equal to the buoyant unit weight of the soil divided by the unit weight of the concrete, that is equal to critical hydraulic gradient in the quicksand condition, no? So this shows that when water flows upward under a hydraulic gradient of about 1, it completely neutralizes the force on account of the weight of particles and thus leaves the particles suspended in water. So we have here, if the water flows upward, no, under a hydraulic, so the condition of a quicksand, it completely neutralizes the force on the account of the weight particles and thus leaves the particles suspended in the water. No. So to better understand is you can search this link now in here and watch. So we have here a soil liquefaction, which is a special, I think this is still a quicksand condition, or yes, a special case of quicksand. In this case, sudden earthquake immediately increase the pore pressure of shallow groundwater, no? Shallow groundwater or katong mabaw lang nga groundwater sa mabaw, no? So actually, mo trigger ang liquefaction when there is earthquake, if especially that the soil is more silty or more fine sandy, more liquefaction na siya. So mabantayan ninyo sa, I think sa Japan, no, there are ay area dito tong Tohoku nga earthquake, naay part dito nga niliquefy ang soil. Ang delikado na siya, especially sa foundation sa soil. Ang mo-fail gyud, no? Mo-fail gyud ang structure. Mulihok naman tong kuan because of the earthquake. So ma-trigger tong sa ilalom, dayon kung silty sand siya or fine sand pa gyud ang yuta, no? mo nang liquefy tendency grabe ang movement na and dili makasupport no sa structure. The saturated liquefied soil loses strength, no? So lose ang strength causing buildings or other objects on that surface to sink. What happens in the I think mooy nahitabo sa Leaning Tower of Pisa, no? Katong building nga incline siya because the foundation on the other side liquefy, no? I mean the soil uh, dito ni liquefy mo to siyang ni sink gamay muna ni incline, no? You can watch this video link, no, attached here to better understand, no, this condition, no, soil liquefaction. So now we will adapt or understand the seepage using graphical solutions or by drawing the flow nets. So the flow lines and equipotentials are at right angles to one another. So this is we have here the flow lines. So if you try to measure the head or the head loss of this each kuan horizontal line, that is the same kuanda head loss or the same hydraulic gradient. We have also these flow lines in the direction of the water in this direction. So the cylinder walls are also flow lines. Distances between the equipotentials are equal. So this line here are the equipotentials, no? Meaning that the head drops between the equipotentials are equal, no? So the principles of flow nets, this is the flow of the water. Now this is the flow of the water. So we have here the equipotential. So this the same distance, no? The same distance. And along the flow of the water is the flow lines. This line here. This part is the flow element, no? Then continuation, no? We have flow line. So as I've said, kung inyo niya siyang butangan o piezometric head, actually the head loss are the same, no? So the equipotential lines, total head loss along this line are the same, no? From the reference line or datum, you have the total head is equal to elevation head plus the pressure head, no? So actually the total head is actually parehara siya, no, for all equipotential lines. So this is the equipotential line perpendicular to the flow line. So this for the seepage calculation from flow net, we have here, if the flow elements are drawn as approximate squares, the drop of piezometric level between any two adjacent equipotential lines is the same. H is the difference head, and N sub D is the number of equipotential energy lost. If the number of flow channels in a flow net is N sub F or NF, the total rate of flow through all channels per unit width can be given as, so for this for the total flow, no, the total rate of flow, that is delta Q through all the channels, is equal to the K, this is the coefficient of permeability, times the H, or this is actually the head loss, no, for each equipotential is equal to I over N sub D, number of potential energy loss, times N sub F, number of flow nets. So we have here flow line, no? We have two flow line here. And say we have the equipotential. So this is the flow element kining apart, no? So that the rate of flow, no, or delta Q is the same, no? That is delta Q1 is equal to delta Q2. And remember that delta Q for the concept is equal to KIA. So that is K times the head loss or delta H over L. So kung square magud siya, because according to here at right angles, then square, no? Approximately squares, no? Approximately square. So using the KIA, no? This is KIA. And I, this is delta H over L. But since this is square man siya, so manang L ang daganan sa path sa tubig. And also, L pod perpendicular distance, that is L1. So manang dayon times area. This should be the area, but times 1 unit width, no? So actually, pwede raman wala. So times 1 unit width mo ng L1. Lagi hapon. Then, makancel ra gihapon, no? Makancel ra gihapon. So that is why the total number of potential head loss. So that is why the total rate of flow, no, delta Q is equal to coefficient of permeability of the soil times the H. That is, since pareha raman siya, H1 minus H2 is just equal to H2 minus H3 or H3 minus H4, so on and so forth. That is, we can denote as general big H over the number of potential energy lost. To better understand, we'll have example later. So this is the asymmetric flow. The intersections are at right angles, no? And approximate to curvilinear square intersections. We have N sub D, or number of pressure drops, no? Number of pressure drops. Flow line, or this is actually the equipotential line, no? Equipotential line, N sub D. And okay, pressure drops between A, B, and CD is H. And let there be N sub D, this is the pressure drops, and N sub F, the flow lines. So from AB to CD, this is total H, no? Divided by the N sub D, which is the number of pressure drops. Alright. So that Q sub F, this is the flow per unit cross-sectional area. This is the flow per unit. This one. No? So this is the formula. Flow per unit cross-section. Hello, Ma'am Weng. Nagklase pa ko, Ma'am. Kadit lang. Manawag ra ko after Nag-klase pa ko, manawag ko after. Sige, sige. So, this is for the flow, no, per unit cross-section. Dayon, the total seepage is actually times na nimo siya pila ka number of flow line, NF times NF. So, this one is seepage around an obstruction. Say this is retaining wall. Then, to better understand the flow of the water, you have to draw a seepage flow line, no? Kani siya. Seepage flow line. Trench supported by sheet piles. Alright. This is a uniform sand in impermeable clay. So, meaning, dili na mulusot ang tubig diri. So that, delta H, this is actually 6 meters because this is the inflow or this is the inflow, then trench. Then, yes, there is inflow, then, kuan siya dire, no? Or in here, dire, padong dire. So, the difference of the height of the water, that is delta H, 6 meters, no? Because this is water and this is water na, no? Or, kaning water, pag sulod niya dire, kani, muning level sa water, so that is 6 meters, no? Difference. Then, NH, this is, ang flow nimo is padong man dito. So, meaning, N sub H, this is the number of the equipotential line. So, if this is the flow of the water, dire. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No? And the flow line, yes, number of flow nets or flow line is 2.5 plus 2.5 times 2 ni siya because this is 1, 2, and half, no? Times 2 because trench man siya. No, this is like for example, this is a obstruction and this is another obstruction, no? So lahi po ang imuhang flow net dire. Unang 2.5 plus 2.5. Another is excavation supported by a sheet pile. This is steel sheet. Let's say this is a retaining wall, no? Sheet pile, water pump away. So again, this is the flow line. Excavation supported by a sheet pile. We have steel sheet, water pump away. No? Okay. I think it's better to have an example. No? Example is the section of the sheet pile is shown in figure. The coefficient of permeability of the soil is 4.2 times 10 to negative 3 meter per second. Excuse me. Determine the seepage into downstream side. This is downstream, no? This is the upstream side per meter length of the sheet pile. We are asked to determine the seepage, that is the Q, no? Q, that is actually volume per second, no? Per meter length of the sheet pile. Per meter length of the sheet pile. So, in per meter meaning the distance, no, into the paper or into the screen, no. Kay nag side view man ta. So kung imo ni siyang i-3D, what is the seepage downstream per meter, no, length of the sheet pile. So we have here a given na kay upstream water, no, 5 meters from the ground surface. Then pag abot nimo sa downstream, 1.5 meters na lang. So first is you have to draw a flow line, no. I think there is a wala siya i-state, but okay, later na. Okay, to determine the Q, the K is given as 4.2 times 10 to the negative 3, no. So using this formula, Q is equal to K times H. This is the difference of this is actually the head loss or difference of the elevation of the water times the number of the flow line time over the number of the equipotential line, no. So munang K is 4.2 times 10 to the negative 10, and number of flow lines is actually 1, 2, and 3 because the flow of water is padong man siya dito, diba? So munang 1, this is 1, 2, and 3. That is why NF is 3. And N sub D, this is number of equipotential like difference, no? We have here 1, 2, 2, 1, 2, 3, this one, 4, 5, and 6. Kani. So munang N sub D is 6. And H is the difference of the pressure head. I mean head, no? Elevation head. It is the head loss, no? If you dumduman ninyo itong Bernoulli's equation, so that is actually just Z, no? Manang 5 minus 1.5, this is actually the distance, no? This is the H. This siya ang H. So, by using this formula, we can have the value of the seepage per meter length of sheet pile in the downstream, no? So for the summary of flow nets, solutions are relatively straightforward. Draw the appropriate flow net. Count the number of pressure drops in the flow net, no, over the relevant distance. Count the number of flow lines. Then do a simple calculation. Work out total flow. Work out pressure at any given point. Then summary of flow net continuation. Rules for drawing flow nets. All impervious boundaries are flow lines, no? Impervious boundaries. So all permeable boundaries are equipotential. So meaning equipotentials, the katong perpendicular siya sa flow sa water. Impervious layer, the flow lines, no? Then phreatic surface pressure is atmospheric, that is excess pressure is 0. Phreatic surface, that is na-expose siya sa like open, no? Meaning the pressure is 0. Change in head. All equipotentials are at right angles to flow lines. All parts of flow net must have same geometric proportions, no? Like rectangle, or that is square or similarly shaped rectangles. Good approximations can be obtained with 4 to 6 flow channels. That is flow to 6, no? Flow channels or flow area, no? Katong square, no? Yeah, more accurate results are possible with a higher number of flow channels, but the time taken goes up in proportion to number of channels. The extra precision is usually not worth the extra effort. So usually the accurate results, no, good or a good approximations, no, using 4 to 6 flow channels or flow area, no, flow channels. So this is the this is the flow line, and this is the equipotentials, no. If the flow of water is padong dito, dito. So this is the channels. Channels is the agian, no, sa water. This one. This one is flow channels. This whole path, flow channels. Ingon siya, 4 to 6 flow channels. So, I think this all for the average, no, coefficient of permeability K and seepage. This is the dam, no, a reservoir. So the flow of the water is from the upstream reservoir to the downstream. So you have to draw, you can have like this one, you can do like that or like that, I don't know. Then this is the flow, this is the flow net, no, this whole drawing is the flow net. Then this is the flow line. Then the channels are kani siya, no, yan. So the n sub f, or number of flow channels is actually 1, 2, 3, 4. That is n sub f. And your n sub d, that is number of equipotentials, that is 1. Actually, equipotential line, pero between ana, muna siya ang n sub d. It is 1, 2, 3, 4, 5, 6. N sub d is equal to 6. So that, I guess that's all, and kindly study na for your midterm examination next week. Bye class.